Have you ever stopped to think about the physics hidden in something as simple as a dripping faucet? Or what about the unbelievable power of a raging river? Well, it turns out that everything that flows, from the water in our pipes to the very air we breathe, is all governed by a really beautiful and powerful set of principles.
So how do we actually go from just watching this stuff happen to predicting it, to harnessing it? How do engineers know how to design a pipe system or how to measure the flow of air? Well, that is the big question we're going to tackle today.
And we're going to build this whole story right from the ground up. We'll start with what a fluid even is, then we'll learn the language to describe its motion. From there, we'll get into Bernoulli's huge idea about energy, and then we'll see it all come together in the real world with things like rivers and dams.
All right, first things first. Before we can understand flow, we really need to get a handle on what a fluid actually is. And a little hint, it's not just about liquids like water.
Okay, think of it like this. If you push on the side of a solid block, it resists you, right? But what happens if you try to push sideways on the surface of water? That's what we call a shear stress. Your hand just moves right through it. And that's the key difference. A fluid, by its very definition, just can't resist that sideways push. It just, well, it flows.
Now, what's really interesting is that not all fluids are created equal. You've got your Newtonian fluids, like water. Its resistance to flow, what we call its viscosity, is always the same. It's predictable. But then you have something like ketchup. It's a non-Newtonian fluid. In the bottle, it's super thick. But when you shake it, when you apply that stress, its viscosity drops and it flows out easily. We call that shear thinning.
These three properties are basically the building blocks for how any fluid behaves. You've got viscosity, which is really just fluid friction. Then there's surface tension, that's what lets bugs walk on water. And capillarity is that cool effect that makes water seem to climb up inside a thin straw. And as you can see, engineers have formulas for all of this, which lets them predict exactly how a fluid is going to act.
Okay, so now we know what a fluid is. How do we actually describe it when it starts to move? Well, physicists and engineers came up with a kind of common language to classify all the different types of flow.
The first big difference is all about time. Is the flow constant? You know, like a river with a nice, consistent current. We call that steady flow. Or is it changing from moment to moment, like that chaotic blast of water when you first crack open a fire hydrant? That's unsteady flow.
The second big difference is about space. So imagine a perfectly straight, man-made canal where the water is flowing at the exact same speed and depth everywhere. That's what we call uniform flow. But a natural river? It gets wider, it gets narrower, and the velocity is changing all over the place. That's non-uniform flow.
And this leads us to a law that is absolutely fundamental, the conservation of mass. We call it the continuity equation, and all it really says is what flows in must flow out. You know this intuitively. Think about putting your thumb over the end of a garden hose. You make the area, A, smaller, so to get the same amount of water out, the velocity, V, has to go way up. Simple idea, but with huge consequences.
Okay, now we're getting to a true giant in the world of fluid mechanics. Daniel Bernoulli gave us a principle that helps explain everything from how an airplane wing works to why a baseball curves. The easiest way to think about Bernoulli's principle is like an energy budget for the fluid. As a little particle of water moves along, its energy might change form. It might swap some pressure for speed or some height for pressure, but the total amount of energy it has always stays the same. It's just the law of conservation of energy, but applied to fluids.
But here's the fine print. Bernoulli's principle is technically only perfect in an ideal world, one with zero friction. In the real world, things like viscosity cause the fluid to lose a little bit of energy along the way. But even with that, this equation is an incredible starting point for almost any problem.
So, when you look at the equation, don't let it scare you. Just think of it as a balancing act. That total head on the right has to stay constant. So if the velocity goes up, meaning the velocity head increases, then either the pressure or the height has to come down to keep the whole thing in balance. That simple trade-off is the absolute core of Bernoulli's idea.
So far, we've mostly been thinking about fluids that are all contained inside of pipes. But what happens when you take the lid off? When you start looking at open channels, like a river or a canal, the rules of the game change in a big way.
Here's the number one difference. What's making the fluid move? In a pipe, it's pressure that's pushing the water along. But in an open river, it's all gravity. The slope of the riverbed is literally pulling the water downhill, and that changes absolutely everything about how we have to analyze it.
So, because gravity is now the star of the show, engineers needed a new kind of tool, and it's called specific energy. As you can see from the formula, it's just a really simple way to tally up the total energy at any given spot, just by adding the water's depth, y, to the energy it has from its velocity.
This whole concept of specific energy leads to something really fascinating. It turns out, for any amount of water flowing, there's one special depth, we call it the critical depth, where the energy is at its absolute minimum. And this depth acts like a crucial tipping point between two totally different ways the water can flow, either slow and deep or fast and shallow. And that tipping point can lead to one of the most powerful, most dramatic things you will ever see in fluid mechanics, the hydraulic jump. It's sudden, it's turbulent, and it is incredibly powerful.
You've probably actually seen a hydraulic jump before, maybe at the bottom of a dam spillway. It's that spot where the super fast shallow water, we call that supercritical flow, suddenly and violently slams into a wall of slow deep water. This crazy transition is basically a standing shock wave, and it burns off a tremendous amount of energy as noise and heat.
Now, what's just incredible is that even though this looks like pure chaos, we can predict it with math. There are really precise equations, like this Belanger equation, that tell you exactly how high the water will jump, from y1 to y2, and that predictive power is what allows engineers to build structures that can actually contain these violent forces safely.
So, after all this theory, why does it all matter? I mean, what does all this complex physics actually let us do out there in the real world?
Well, pretty much everything. Every single one of these applications is a direct result of the principles we've just talked about. A Venturi meter uses Bernoulli's principle to measure flow. A turbine is designed to perfectly capture the energy in moving water. And those giant concrete pools at the bottom of dams, they're called stilling basins, and they are built for one reason: to create and contain a hydraulic jump, safely getting rid of energy that would otherwise tear the whole riverbed apart.
So, from a simple little equation all the way to massive hydroelectric dams, the principles of fluid mechanics are literally all around us. They have helped us build our entire modern world. And when you think about the challenges we're facing now with energy and climate, it really makes you wonder, what new problems are we going to solve with these same ideas next?